Hi, everyone. Thanks, Luke, for the introduction. I guess I'll start with the icebreaker too. Or well, maybe first with an introduction. So I'm Alex Hentschel. My current role is Chief Protocol Architect for the Flow Foundation. And my focus is very in detail the protocol layer of Flow. I mean, there are more layers like Cadence and then the ecosystem layer and a few more layers at the bottom, which goes into hardware. Dieter sort of owns the entire stack. He's the architect for the entire stack. My focus is literally just the protocol, which I think is also a pretty hairy detail. So my background is applied mathematics. I joined Actium then, the parent company of DARPA Labs, in 2017. And my first touch point with crypto was when CryptoKitties launched. Some other folks at the company were working on CryptoKitties, and I was being looped in to make a player analysis based on the user's in-game actions and to group them into sort of cohorts of what they do. Yeah, so that was sort of the first area where I really got into the mechanics of crypto. And then I started reading the papers. As somebody who's interested in applied mathematics and algorithms, that was relatively intriguing material for me. I'm not sure if you remember, but like early 2018, consensus hadn't been developed that far. Tendermint was released, but hot stuff hadn't really gotten traction. I don't think the paper was even released or was released around that time. I started reading Definity's paper on secure random beacon. And I found that all super intriguing and interesting from a technical perspective. So I got like progressively deeper into the topic. So today, I want to pass on a little bit of the things I've learned over the last 5 years, and I'm going to talk about modular blockchains. So this is supposed to be about roughly a 15-minute talk, and at the end, I hope you're all going to be expert on modular blockchains, so I hope you enjoy the ride. And to ease into the topic, let's start with the conventional monolithic architecture. That's what I would like to call it. So the blue box here in the middle, that's typically what we consider a node. Internally, that node has several sort of functional layers. There's data ingestion at the bottom, consensus above, which agrees on the transaction order. Then there's transaction execution, and then the results are indexed. And the protocol typically engages on the consensus and the transaction execution layer. The node gets a block, it looks at the block, says, oh, those are the transactions, it executes the transactions, confirms that it has the right result or a matching result, and then sends a message to the network saying that it agrees. While the users, they engage in tendency more on the outside layers. So they feed data into the mempool. That's what I call the data ingestion layer, or they recall data from the node about what happened with transactions. And one thing which is very important here to note is that all those layers here internally, they all happen within the node. And of course, you know, the software within the node trusts itself. While if you go outside of the node and talk to either clients or other nodes in the blockchain, you have to potentially talk to malicious peers, right? It's a completely open system, so anyone can run a node, including malicious parties. And so when you do those node external data exchanges, you have to use cryptography to make sure that first you authenticate your data properly, so other people, in case they don't agree with you, have a means to challenge and say, hey, I think you did something different than I, and I disagree with that, and same with the clients. So there is some computational or a decent computational overhead involved. And in addition, of course, you know, talking to other nodes in the network, that usually means you're talking to a server which is halfway around the world. And that also has some latency costs attached to it. Great. So those are modular those are monolithic blockchain architectures. One of the key features here for the monolithic blockchains is that all the logic for the protocol is one gigantic block, right? You get the block and you say you either agree or you don't agree with it. There is literally nothing what happened, no data exchange in between. And that makes the platform highly integrated, right? So anyone interacting with it, they're interacting with the entire protocol stack. The protocol stack is designed as a whole, and people get a sort of holistic, integrated user experience, which is great. So one of the pros of this architecture, as I mentioned, is a cohesive user experience. It's also the cohesive developer experience, right? The developer has to deal with one protocol and only that one protocol. And since every node does everything, every node knows the entire execution state, and smart contracts within that execution state can easily interact. So we call that smart contract composability. And that helps the ecosystem as a whole to evolve. Like open source, people can use other people's smart contracts and sort of call them and interact with them. And so the ecosystem as a whole becomes more than just the sum of its parts. The challenges, of course, are that this architecture has trouble scaling beyond the capacity of a single machine. You know, every node does everything. So as soon as whatever you want to do doesn't fit in that node anymore, you're in trouble. The other aspect is sustainability. Typically, we want very many nodes for Byzantine fault tolerance and just decentralization. And if all those nodes, maybe let's say 1,000, they all do the same thing, then you literally have 1,000 times the hardware and energy consumption as if you just ran that same computation on a single server in like a cloud computer or a cloud platform. So those are the, I think, relatively well-known challenges of monolithic architectures. So let's look at the more recent sort of evolution. What we see is we see a more modular architecture or more modular platform. At the bottom, you have the data ingestion layers. Yeah, I think it's maybe worthwhile to think or talk a little bit about how Ethereum is approaching this. So, for instance, in Ethereum, they've considered data availability shards like EigenDA. That is one example where some, I guess, semi-independent organization is developing their own solution and is providing one of those data ingestion shards. A more recent development in the Ethereum community is dunk sharding. It's conceptually relatively similar, that only a subsection of the nodes kind of hold the data, but it's not like a predefined group. It sort of changes dynamically throughout the course of consensus. So it's kind of merged partially into this consensus or into the consensus algorithm. So that's the reason why I've drawn it that the data ingestion in this example kind of blends into the consensus. So you have the data ingestion layer at the bottom, and then you have consensus. Above the consensus is the execution layer. And I think there's something very important here to notice. That is, so in the prior example of the monolithic architecture, the main central or one of the main central goals for consensus was to agree on the correctness of a result. And that is not quite the case here anymore. So consensus might provide a reference frame for transaction ordering. It orchestrates the higher layers and the lower layers. It's also very important for reconciliation. So if there's some disagreement what the correct result is, usually that's sort of escalated to the central consensus layer. But consensus doesn't really agree on the sort of execution state anymore. It sort of records it and it tests that somebody has told that this is the correct or that this is the result, but it doesn't guarantee itself correctness anymore. So where does the correctness in this architecture come from? Well, like the Ethereum ecosystem has multiple options, which is really great. They can develop independently, and we can see what sort of gains traction what gains traction. So one of the areas, you see that here to the right, is the typical L2 optimistic roll-up sort of construction. You have a validity guarantee. The left one is the optimistic roll-up. I'm sorry. So you have a social validity, either a social validity guarantee that people just know the person who's running the sequencer, or maybe they're running outside of the protocol, they're rerunning the transactions, and then they have a larger time window to disagree and maybe submit a fault proof. So in a certain way, the protocol itself has no hard means of validating the result. It's sort of left to the social layer outside of the blockchain protocol. The middle version here is, for instance, validity proofs through zero knowledge. That is also a relatively promising approach, in my opinion. Challenges are that zero knowledge isn't quite as far developed to be really fast enough for general computation. So I assume we'll see more sort of specialized zero knowledge app chains and L2s there, which can do a subset of general computation, maybe only money transfers or things like that very well. But if you want just to write a general purpose smart contract, it might be that zero knowledge layer or zero knowledge execution stacks are either too slow or they don't support it at all. And then there's, on the right hand, we have validity guarantees through protocol, I guess, internal or protocol mandated re-execution. So that's like Arbitrum, TrueBit, where they have a specific verification stage. And that verification stage guarantees that after a result has passed that verification stage, it's guaranteed to be correct. So that's great. You know, we have various solutions and they can evolve independently, and we can see which solution maybe wins. All right. So the pros of this solution is that one of the big pros here is that the data ingestion and execution scales horizontally beyond a single machine. That's a huge breakthrough. Remember, the monolithic architectures before, they were kind of bound to the limitations of a single machine. Here, we have horizontal scaling on data ingestion and execution. And another hugely advantageous aspect in this design is that we can independently tune the redundancy. For instance, you could have 50 execution layer or 50 execution stacks and 200 data availability shards. You know, so depending on where you need more machine power, you can scale that part of the system. In a monolithic architecture, you always need to scale the entire system, which kind of increases your energy and hardware consumption. I call this architecture here a modular architecture because it has individual building blocks. But I think the platform is federated. What I mean with federated is that you have largely independent entities making their own rules about what is happening in their specific part. For instance, you know, some data availability layers might have other rules, other costs, other sort of APIs. Same is for the execution environment. We've already talked about some zero knowledge execution stacks only supporting a limited number of instructions, being specialized, you know, others guaranteeing validity in protocol, others relying on outside validation. We have different EVM dialects. All this sort of is, so you have little zones with somewhat independent rules. And so the optimal application scenario for this thing here is many computationally independent ecosystems, which have very limited data exchange and functional integration. So let's pause a little bit here and pay attention to that detail of limited data exchange and limited functional integration. As we've talked about earlier, when you cross, you know, those Byzantine boundaries here from one node to a different node that don't trust each other, you incur computational and latency overhead, massive computational and latency overhead. So that means If you're running a smart contract in one of those execution stacks and you want to communicate exchange data with a smart contract in a different execution stack, that's going to be costly and relatively difficult for any developer to implement, because they suddenly need to understand both stacks, right? And you can see the more stacks you want to interoperate with, the more you want to compose logic beyond what fits in a single execution stack, the more the complexity grows for the developer. And complexity increase usually also means more security risks. And it's not quite understood how Web3 composability at scale can happen in such an architecture, because in the end, each of those individual execution stacks, that they still have to fit in one machine. So what do you want to do if you have like 20 terabytes of state? Maybe that's a useful application, but you can't run this application on one of those execution stacks in here, because the execution stacks individually don't scale to this extent. So developer complexity and composability are the biggest challenges for federated modular architecture. Let's go to the next slide here. So one of the, or at least for me, that was a relatively profound insight. If you look at conventional cloud platforms, they're also super modular, right? It's like different software stacks, but the platform experience for developers and users is highly integrated. It's not federated, right? If you go to AWS, you get through AWS, you get the databases, the storage, the compute, everything. You get that all through one integrated user experience. You don't have to learn 20 different dialects of stuff just to sort of spin up your microcosm of some functions. And I think that is something very important to keep in mind, because in the end, we want an ecosystem that is easy and safe for users to use and easy for developers to develop for, because then they can focus on the stuff which really makes a difference. They're not bogged down with understanding how system A versus system B works. They can really just sort of innovate and create and iterate. And so ideally, we would also like to see such properties in a blockchain. So let's go through a thought experiment here, a really short one, to see how an integrated modular architecture could look like. So we still want a protocol which is composed of modular components. We've already talked about that the data ingestion in this model, horizontally scaling, either be it data availability shards or something like dunk sharding, that works well. We have consensus as a reconciliation layer and an orchestration layer. That also works great. The challenges we have with user experience, developer experience, and sort of composability, they happen at the execution layer. So that's the sort of two top layers here. So let's take a closer look there. So if you zoom into one of those execution stacks, like reasonable values for a decentralized system could be something like maybe 3 to 10 redundant sequencers. I call them execution nodes here, and maybe 20 verification nodes. If you go much below that, you're already running into the challenges of decentralization. Optimism has like a great roadmap. That's where they want to get through, right? They want to get to execution nodes or sequencers which check each other's results. So in a sense, execution verification is one functional block, but it still exists. TrueBit and Arbitrum have a similar sort of design. So that's great. But now let's think about what we would have to do to change from a federated system where you have all those individual gray boxes, each slightly working differently. How do you get that into one cohesive user experience? And Flow's answer, that's where we're getting to Flow's architecture, is to localize all that computation in one or in few execution nodes. And there's a really, really important detail here. If we go back, if you're communicating between those little like execution shards, you're crossing a Byzantine boundary. You have computational latency overhead, which limits your composability. If you go into this design here, where all those little components run, for instance, as microservices, mutually trusting each other within an execution node, then you don't have that Byzantine fault-tolerant overhead anymore for communication. No latency, they're all running in the same data center. So we're essentially keeping the 8 execution. So in the old, or not the old, in the prior design, we had like 8 execution nodes here in each of those stacks, right? And so we're now just keeping the same thing, 8 execution nodes, but make each execution node serve all the stacks. So that's in this architecture, each of the execution nodes is serving all the little execution sort of microcosms. Great reduction in latency and computational overhead. And so now the question is, well, what's with the verification? With the verification, we had 20 verification nodes maybe for one of those little execution microcosms. And that is great. Though the subtle challenge is that if you want to attack that execution microcosm, you know exactly which 20 verification nodes you have to take out. So it sort of limits a little bit the Byzantine fault tolerance. If you really dive into the math, you'll see that it's much better to just have all the verification nodes the same number and the same load, but just randomly assign them to take random parts of the computation. So the machines and their energy consumption stays the same, but now it's much harder for an attacker to predict which nodes they have to attack and take out in order to compromise a certain system functionality. And in fact, it's more or less intractable. You know, your chances are so astronomically low that it doesn't really make sense. So not only do you get better sort of efficiency through localizing the execution by sort of throwing all the verification nodes into one pot and have them serve the entire execution, you get a much stronger Byzantine fault tolerance. And then in Flow's architecture, we have the edge network on top, which is just related to or responsible for moving the data outside to the clients at scale. All right, now we're almost through. Yeah, we've talked about sort of the stack here that forms Flow's integrated processing pipeline. We independently can tune the redundancy for all the levels to maximize efficiency without breaking decentralization or composability. So in summary, the game changers of this integrated modular architecture is it supports massive composability. There is a huge complexity reduction for developers and users because they only integrate with, or they only interact with one integrated platform. There are enormous sustainability and efficiency gains because all the execution is localized in the execution node, doesn't have to cross Byzantine fault tolerant boundaries. The only challenge is that, of course, an integrated platform requires more coordination and alignment during its implementation. And so it's a little bit harder to sort of go into this Ethereum model of sort of just an organic evolution where a bunch of independent teams do their thing and you figure out what works best in the end. But as I said, it has huge advantages in terms of usage and sustainability. Okay, if what I talked about piqued your interest or sparked your interest, and you want to learn more, go to our website. Under Learn, Core Protocol, there's a Core Protocol vision, which goes into much more detail about what I've just talked about. You can read up all the details, see all the references. It's a relatively scientific discourse there, which, hopefully you will enjoy reading. We also have a piece on data availability, how that scales horizontally. If you want to, please join us and build with us this amazing system. We have the core protocol working group. It's open for everyone to attend. We'll sort of talk about similar things at the technical level as what I've just presented. And I would be super excited to have you join. I'll be there heading that group, and then many of our very, very capable and smart engineers will also be there. And I think that's it from me. Thank you, and handing it back to Luke.
Thank you, Alex. That was absolutely incredible, as always. I mean, some of it goes over my head, so I'll probably have to watch it back later, but I do super appreciate the explanation. I think you broke down some really complicated stuff in a very easy to understand way.